This is the last lecture of chapter 4, which deals with chemical reactions. As a quick review before we start, last lecture we looked at chemical reactions. In terms of, by definition, what are chemical reactions? And next we looked at balancing equations or reactions, which means that on the left side of the reaction, the atoms and type atoms must equal the type atoms and number atoms on the right side, which is the products. So we balance equations by using coefficients. Notice they are coefficients, not subscripts, but coefficients just prior to or just outside of the different reagents or prefix. Next, we looked at type reactions. As we said last lecture, there are different type reactions that exist, and we can break them down into categories. And two categories that we looked at were reactions involving ions, which means the cations and the anions in solution. And we also looked at a very important type reaction, which is reduction and oxidation, also known as redox reaction. In today's lecture, we will look at formula weights of compounds. Okay, we'll also look at the mole and molar mass. You'll discover this is essentially the unit of chemistry, the mole. We'll look at stoichiometry. We'll define stoichiometry, which is the relationship, the mass relationship of reactants and products in a reaction. We'll look at percent yield for different reactions. And we look at heat gained or loss that accompany various reactions. For this lecture, you will definitely need your periodic table and a calculator. So my suggestion at this point is to pause the video and go and find your periodic table, have it right beside you as you work and read along, and have your calculator, because we'll be doing a few calculations. Okay, let's get started. First, we'll look at formula weight. As you know from the periodic table, just about every matter consists of, I shouldn't say just about, every matter, in fact, consists of elements shown on the periodic table. It just so happens that they are combined in different fixed, the key here is fixed ratios. And they form compounds. So the elements combine in fixed ratios to form compounds. It's very important to know the formula weight of these compounds, which essentially is the sum of the atomic weights. As you can see here, the sum of the atomic weights of the atoms of these compounds will be the formula weight. We will use that a lot in our calculations. So let us use an example here. So for example, if you're asked to calculate the formula weight of the ionic compound sodium chloride, you'd look at your periodic table and you'll find sodium, and you'll decide what is the atomic weight of sodium from the periodic table. Same for chlorine. You'll find chlorine and you will look at the atomic weight of chlorine and you add them. Notice the units here. It's AMU, or atomic mass units. As you may recall from previous lecture, these atoms are so light that we do not use grams. So we have a different unit for them, and we say it's the atomic mass unit. So the formula weight of sodium chloride is 58.5 AMUs. Another example here is water. It's 18 AMU, so you add 2 hydrogens and 1 oxygen, or the atomic weights of these, and you get 18.0 AMUs. Aspirin, which of course we're all familiar with, if we have a headache, that's what we take. This is the molecular formula here, and you can see it's 9 carbons, 8 hydrogens, and 4 oxygens. Still have to multiply carbon from the periodic table, which is 12.01 times 9, hydrogen multiplied by 8, oxygen, which turns out to be 16.00, multiply that by 4, and add those up, and what you will get here is 180 AMUs. Notice here we have 2 types of compounds: ionic compounds, which means they have a cation and an anion forming that bond. And here we have molecular compounds, which means essentially that the bonds are covalent bonds. So I'm mentioning that because we have 2 terms here. Formula weight are typically reserved for ionic compounds, and molecular weight is a term that's typically reserved for covalent compounds. In this lecture and in this book, they will be used as synonyms. So formula weights here will mean the same as molecular weight. Okay, let us look here at a concept, and this is the concept of the mole. And follow me carefully here, because we'll have to develop this concept here and comprehend this concept and appreciate this concept before we can start applying it. So let us look at what's shown here. Let us imagine that we have 1 gram of, I don't know, let's say iron, and 1 gram of carbon. So the question is, do you think that in this 1 gram of iron there is the same number of atoms as in 1 gram of carbon? Think about that carefully. Remember, one aspect of this course is really thinking and analyzing stuff. So 1 gram of iron, will 1 gram of iron have the same number of atoms as 1 gram of carbon? Looking at the periodic table, you can see that the atomic weight of iron is 55.85. It's pretty heavy compared to the carbon, which has an atomic weight of 12.01, much lighter. So therefore, if you had 1 gram of iron and 1 gram of carbon, you probably would expect less number of atoms of iron compared to that of carbon, because iron is heavier than carbon. So the bottom line is that when a reaction occurs, it does not occur in terms of grams, but it occurs in terms of atoms reacting with atoms. So let us apply this and get a new definition here. The definition of the mole is that if we have 1 mole of iron atoms and 1 mole of methane molecule, which is CH4, or even 1 mole of sodium ions, which is on your periodic table to the left, they contain the same number of formular units. And let us emphasize here atoms. So let's rephrase that just to make sure we understand it. If we have 1 mole of iron and 1 mole of carbon, for example, they have the same number of atoms. As we stated earlier, if we have 1 gram of iron and 1 gram of carbon, they will not have the same number of atoms based on the difference in weights. So the unit that we're concerned with here is a new unit called the mole, and what it means is that 1 mole of anything will have the same number of units, call it atoms or ions or molecules, as 1 mole of another substance. Okay? Let's take it further. The number of formula units, such as atoms, in a mole is known as Avogadro's number. So we can physically measure how many atoms are there in a mole of substance. For example, iron. Avogadro's number is right here. 6.02214199 times 10 to the 23rd, or 6.02 times 10 to the 23rd. So there are 6.02 times 10 to the 23rd units, could be atoms, in 1 mole of anything. Okay, so just think about that for a second. That becomes a conversion factor, which we'll use later on. Another definition of the mole, which we will not use as much, but it's one that's also make reference to, is a mole of any substance is that contain as many atoms, molecules, or ions in exactly 12.0 grams of carbon-12. In other words, what they're saying here is that if you had the isotope carbon-12 and you had 1 mole of carbon-12, it will contain the same number of atoms and units as 1 mole of any other substance. Okay, let's see if we can apply that concept. So here let's define molar mass. So now that we have understood the mole is, of course, the number of units, molecules, ions in a substance. Now let's look at the formula weight of the substance. This is the molar mass. The molar mass is the formula weight expressed in grams. Notice the units, grams per mole. So therefore, if we have glucose, here is the formula. If we calculate the formula weight by adding up all the atoms or the atomic weights, what we have is 180 AMUs. This is now the molar mass of glucose is 180 grams per mole. Grams per mole. What this is really saying is that in 1 mole of glucose, it has a mass of 180 grams. So let me repeat that. So let me repeat it in a different way. So if you have 180 grams of glucose, it is 1 mole of glucose. Another way of stating that, 1 mole of glucose weighs 180 grams. So that's called the molar mass. Here's another example before we move on. Urea. This is the molecular weight, molecular formula. So now you can see the importance of molecular formulas, which is the fixed ratio of the atoms in a molecule. So here is the formula. From the formula, and using your periodic table, you can determine the molecular weight. And here it is, 60.0 AMUs. Notice the unit, atomic mass unit. The molar mass of urea is 60.0 2.0 grams per mole, which means that 1 mole of urea will weigh 60 grams, or 60 grams of urea is 1 mole. Notice again that 1 mole of urea and 1 mole of glucose weighs different. They have different weights. All right? So the importance here is, shown over here, is that when you go in the lab, you don't weigh out 1 mole of a substance because you don't have a balance to weigh 1 mole. What you have is a balance to weigh grams. So oftentimes we have to convert grams to moles. And we'll see why in a second. Well, I'll tell you, because for reactions that take place not in terms of grams, but in terms of moles. So we often have to convert grams to moles. Here's the conversion factor. The conversion factor is 1 mole of anything is equal to the molecular mass in grams. As we said from the previous slide, 1 mole of urea is equal to its molecular mass in grams. 1 mole of glucose is equal to its molecular weight in grams. So let's see if we can apply that here. So calculate the number of moles of water in 36 grams of water. So if you had 36 grams of water, so you went in the lab and you weighed out 36 grams of water. The question now is, how many moles of water do you have? I hope you're getting the sense that the mole is really our unit. So more than likely you will have to convert just about all weights, everything, back to the mole. So here's our conversion factor. So we know that 1 mole of water is equal to 18.0 grams of water, because that is the molecular weight of water. So this is our conversion factor right here. And we have 36.0 grams of water. We set up our conversion factor so that these numbers cancel out, and we end up with, over here, moles. So we have 2.0 moles of water. Bottom line, 36 grams of water is equal to 2.0 moles of water. Let us do some more applications here. What is the number of moles in 36 grams of sodium sulfate? So your first question is, what is the formula of sodium sulfate? Here it is. So the first thing you need to do here is to take the molecular formula and determine the molecular weight. So get your calculators and get your periodic table. Find sodium, which is 23, multiply it by 2. Find sulfur, which is 32.1, and add that to oxygen. Find oxygen, which is 16, and multiply it by 4, because we have 4 oxygens. Then, of course, you add those up, and you should get 142.1 AMUs. So that is the molecular weight of sodium sulfate. Next, we need to find out the number of moles in 5.3 grams. Here is our conversion factor. 1 mole of anything, in this case sodium sulfate, is equal to the molecular weight of anything, in this case sodium sulfate. We set up our conversion factor right here, because 1 mole of sodium sulfate is equal to its molecular weight in grams, 142.1. And we have 5.63 grams. So we set that up so that the grams cancel grams, and we multiply 1 by that and divide it by 142, and we end up with 0.0396 moles of sodium sulfate. Conclusion: 5.6 grams of sodium sulfate has 0.0396 moles, or equivalent to 0.0396 moles of sodium sulfate. Okay, let us do another example here. Aspirin. So the question now is, if we have 0.360, so one tablet of aspirin contains about 0.360 grams of aspirin. How many molecules? Notice this is a little different. It's not asking for how many moles. How many molecules? Which means that you'll have to convert that to moles and then determine how many molecules are in that mole. So first of all, we have to determine the molecular weight of aspirin. Here it is. Next, we have to do the conversion into moles. Here's our conversion factor right here. 1 mole of aspirin is equal to its molecular weight, 180 in grams. We set that up so that the grams cancel grams, and we multiply by 0.360 divided by 180, and that's equal to this number of moles. So that's the number of moles that are present in 0.36 grams. But the question is not asking for how many moles are present. It's asking for how many molecules are present. So we need another conversion factor. The conversion factor here is 1 mole of aspirin has Avogadro's number in terms of molecules. So 1 mole of aspirin is equal to 6.02 times 10 to the 23rd molecules of aspirin. So notice, a lot of conversion factors are used to determine what we're looking for. So we set this up. Here's our conversion factor here. 6.02 times 10 to the 23rd molecules and 1 mole. It should be 1 mole here. And we have 0.0200 moles. Moles cancel mole. And we multiply this number by 6.023. Don't forget, you use your calculator here to get the scientific notation here. And this represents the number of molecules, because we still have molecules uncancelled in our equation. So again, be careful. Read your question carefully to determine what's being asked. And more than likely, or 99% of the time, you will have to convert grams to moles. So let's think of converting everything to moles, because as chemists, we work in terms of moles. That's our unit. Okay. Stoichiometry. And a new term for us, stoichiometry, is the study of the mass relationship in an equation. You may recall last lecture we looked at balancing an equation, because what that means is that gives us the atomic relationship between the reactants and the product. So let us look at this reaction here, hypothetical reaction. The products, the reactants on the left react to form the products on the right. What this is saying is that A plus B reacts to give products C plus D. What actually occurs, however, is that it is not 1 gram of A that's reacting with 1 gram of B. That is not the case, because we know that reactions take place at the atomic level. That's why we balance the equation to make sure that the atoms on the left equal the atoms on the right. So what really happens is 1 mole, because this is the one right here, 1 mole of A reacts with 1 mole of B to form 1 mole of, by the way, this should be C, and 1 mole of D products. So again, the main thing here is that reactions take place at the atomic level. And we use the unit of moles, 1 mole. So not grams. So don't be confused. If you are given grams, you will have to convert that into moles. Okay, let's apply that. So here's an application. How many moles of nitrogen, here's nitrogen, are required to produce 2 moles of ammonia? So what we need here is the balance. Notice keyword balanced equation. So if it's not balanced, you will have to balance it. That's stoichiometry. Dealing with the mass relationship from the balanced equation. So the equation here is balanced. So the question is, how many moles of nitrogen, if reacted with hydrogen, gives us 2 moles, here's a 2 moles of ammonia. From this equation, we have a conversion factor. The conversion factor is 1 mole of nitrogen. Here's a 1, don't forget, the 1 is not written, but it's understood, gives 2 moles of ammonia. So that's a conversion. 1 mole of nitrogen reacts to give 2 moles of ammonia. So therefore the answer is 1 mole of nitrogen. Okay? So of course, if I'd ask you how many moles are required to give 4 moles of ammonia, that would be 2 moles, because using this conversion factor. So it would be 2 moles of nitrogen would be required to give 4 moles of ammonia. So again, you'll have to use the moles here to solve these problems. Let us take it a step further. Given the balanced equation, notice we always have to use the balanced equation. Now you can see why we emphasized in the previous lecture and quiz how to balance the equation. So the question is, how many moles of nitrogen are required to produce 7.5 grams of ammonia? Notice we're not asking here for moles of ammonia as we did the last question. Now we're given grams. So as you can imagine, we're going to have to convert this into moles at some point. So make sure the equation is balanced, and it is balanced. So the first thing we need to do is to find the number of moles of ammonia. Okay, we know the conversion factor is right here. We know that 1 mole of ammonia is equal to 17.0 grams of ammonia. Why 17? Because this is the molecular weight of ammonia. We set up our conversion factors so that grams cancel out because we need moles as our answer. So 7.5 divided by 17, we have here 0.44 moles of ammonia. So that's how many? So 7.5 grams is equal to 0.44 moles of ammonia. So now the question becomes, how many moles of nitrogen? Conversion factor is still the same from our balanced equation. 1 mole of nitrogen gives 2 moles of ammonia. So we set up our conversion factor here. 1 mole of nitrogen gives 2 moles of ammonia. We set that up so that ammonia cancels out because we really need nitrogen. So multiply 0.44 times 1 divided by 2 equals 0.22. So conclusion, we need 0.22 moles of nitrogen to give 0.44 moles of ammonia, and 0.44 moles of ammonia is really 7.5 grams of ammonia. So you can see here, we're going to be constantly converting from grams to moles and moles to grams. So make sure you have that conversion factor and know how to use it. Okay, let's take it a step further. Now the question is, how many grams of nitrogen? Grams. We're not asking now how many moles. How many grams? So thinking ahead, you're going to convert everything to moles, carry out the reaction, and then convert your moles back to grams. So let's see, we have the same 7.5 grams of ammonia that's needed. So we convert here the 7.5 grams to moles, as we did before. 0.44 moles of ammonia. We know that it takes 1 mole of nitrogen to give 2 moles of ammonia. Here's a conversion factor here. We set that up. So what we have is 0.22 moles of nitrogen is needed to give 7.5 grams of ammonia. But the question asks for how many grams. So we're going to have to convert this mole into grams. Here's the conversion factor. 1 mole of nitrogen is equal to the molecular weight of nitrogen. So look at your periodic table. You'll see N on the periodic table. It is 14 on the periodic table, but we have here 2 nitrogens. So it's 14 times 2, and that's why it ends up to be 28 for N2. And of course we set that up so these cancel out because we're trying to find grams. Then you multiply 0.22 times 28.0 and you get 6.16 grams of nitrogen. Conclusion, it takes 6.16 grams of nitrogen to react using this equation here to give 7.5 grams of ammonia. So now you can see how they do this in industry. Of course, as you know, ammonia is used as a fertilizer, as a salt, of course, ammonium. And so a company has to produce X amount of kilograms of ammonia. And so they have to first calculate it at the molar level and then take it back to grams. So that's one of the importance in industry of converting moles to grams and grams to moles. Let us look at another concept here called limiting reagent. Let's define it first and then we'll apply it. So limiting reagent is the reagent that's used up first in a reaction. So typically, if you have A plus B in a reaction, typically one is in excess. One of the reactants is in excess and the other one is not, so that it's used up. And the limiting reagent is the one that's used up first. So let's look at this reaction here. For this reaction here, we're reacting nitrogen and oxygen to give NO, nitrous oxide. Of course, as you need to check to make sure it's balanced, and we have 1 here, so that's 2 nitrogen. We have 1 here, so that's 2 oxygens. So we have 2 here for 2 nitrogens and 2 oxygens. So that's balanced. Always check to make sure your equation is balanced. Okay, so before the reaction starts, if you have 5 moles of nitrogen and 1 mole of oxygen, that's before the reaction starts, you have no product. Once the reaction occurs, after the reaction is done, you can see that 1 mole of oxygen will be used up, using up 1 mole of your 5 moles of nitrogen, leaving 4 behind to give here 2 moles of your product. Bottom line is we're concentrating on our reactants. So oxygen is our limiting reagent because that is used up in the reaction and leaving behind nitrogen in an excess. So, conclusion. Oxygen is our limiting reagent. Again, you'll see that term quite a bit. Limiting reagent is just the reagent or the reactant that's used up first in a reaction. And of course, the other one is the reactant or reagent in excess. Let us look at another example here. So if 12 grams of carbon are mixed with 64 grams of oxygen, what is the limiting reagent? So again, whenever you get these questions on the quiz or on the test, make sure that you understand the question, what's being asked, and try to solve it based on information given. So notice these are given in grams, not in moles. So as you can imagine, your first job is to convert grams to moles. Always convert grams to moles. That's the unit of chemistry. So let's set up a little table here. So before the reaction, we have 12 grams of carbon right here. And we have 64 grams of oxygen right here. And we do not have any product because that's before the reaction occurs. Next, we have to convert to moles. So this is 1 mole of carbon and 2 moles of oxygen. I hope you remember how to convert grams to moles. Here is our conversion unit here. 1 mole of anything, carbon, is equal to the molecular weight of carbon expressed in grams. So we get here 1 mole of carbon and 2 moles of oxygen from 64 grams. We still do not have any product because we're just doing the calculation. After the reaction occurs though, since it's a 1-to-1 reaction, what we have here, 1 mole of carbon will react with 1 mole of oxygen, leaving behind 1 mole of oxygen to produce 1 mole of carbon dioxide. If you want to convert this back to grams, you can, but as you can see here, carbon is used up first, so therefore in the above situation, carbon is the limiting reagent and oxygen is used in excess. So once again, you should be able to define what is a limiting reagent, get that concept, and you should be able to apply it to a reaction such as this one. Let us introduce another concept here, and that is percent yield. In the research lab and in industry, whenever a reaction is performed, typically there are side products. So you get your product that you're trying to make and other products. But you will have to isolate the product that you really want and calculate how much of that product you actually got. So what's done here is we have an equation called the percent yield, which actually tells us how well that reaction went to produce as much of the product that we wanted. So here's the equation. Percent yield is equal to the actual yield. That's what you actually isolated. So you did the experiment and you actually isolated that yield, divided by the theoretical yield. The theoretical yield is what you predicted it should have been based on the stoichiometry. So based on the stoichiometry, you have a theoretical yield as shown here. That's what you should have gotten. But the actual yield is what you actually got. Right? That means you did the reaction, you did your best at this reaction, but you did not get what you expected. You did not get the amount that you expected. So the percent yield can give us an idea. So here's the equation. Actual yield divided by theoretical yield. Now this can be in moles. I suggest using moles because that's the unit that we have. But you can also use grams, but be careful here though, because we will have to make sure that the actual yield in grams and compare that to the theoretical yield in grams. So I'm going to suggest using this equation here since we are emphasizing moles. Let's apply that and see how it works. So suppose we mix 32 grams of methanol. This is it right here. With an excess of carbon monoxide. This is it right here. And we're trying to make here acetic acid. And this is acetic acid right here. And the question is, how much acetic acid should we get? And what is the percent yield? So let's make sure we understand the question. So we went in the lab, we bought some methanol, 32 grams of methanol, and our boss said to us, working in an industry, we're going to make acetic acid and sell it. Let's see if you can make as much acetic acid as possible. So you get 32 grams of methanol, and you need to obtain 58.7 well, after the reaction you obtained only 58.7 grams of acetic acid. Let me say that again. I think I mixed that up. So suppose we have 32 grams of methanol and your job is to obtain 58.7 grams of acetic acid. Your job is to obtain as much acetic acid as you can, but you obtain only 58.7. Okay? Let's reemphasize. When in the lab, you had 32 grams of methanol. Your job is to obtain as much acetic acid as possible. But you actually obtained here 58.7. How good was that experiment? What was the percent yield? So let's set up this table. Methanol is here. We have 32 grams. Here it is. And there's an excess, so we need not worry about carbon monoxide. Before the reaction, we do not have any acetic acid. We convert that to moles. So before the reaction, we have 1 mole of methanol. Again, hopefully you remember how to convert grams to mole. We need not worry about carbon monoxide because that's 0. And of course, the product here is 0. Theoretically, we would expect from the stoichiometry, when the reaction is done, 0 moles of methanol and 1 mole of acetic acid. Notice this is this theoretical expectation. And by the way, this should be in moles. Theoretically, we would expect here 0 mole of methanol when the reaction is done and 1 mole of acetic acid. Theoretical. I mentioned you can do it in grams, but let's not worry too much about that just yet. Let's work in moles. We actually got, however, here as our product 58 grams of acetic acid, 58.7 grams of acetic acid. We're going to convert that to moles. So we actually got 0.98 moles of acetic acid. The percent yield would be this number divided by this number. Let's make sure you can see it. Times 100 using the equation on the previous slide. And we got 97.8. So the bottom line is that experiment was pretty good because we got a pretty high percent yield. A pretty high percentage yield. So let's do a quick review and summary. So you went in the lab, you have 32 grams of methanol. Your job was to produce as much acetic acid as possible. But you actually actually isolated. Notice the word here is actually isolated. Actual yield, 58.7 grams. What is the percent yield? Set up this table here before the reaction. You have this grams converted to moles. And over in the product side, your theoretical yield based on the stoichiometry is shown here. And then you convert, and then you determine your actual amount based on what's isolated. Convert that to moles, right? And then use the equation on the previous slide here. As you can see here, the actual yield divided by theoretical times 100. And what you will get over here is 97.8%. Okay, last slide is heats of reaction. So, as you know, whenever spring and summertime coming up, you go to the hardware store and you buy your propane gas and you connect it to your grill and you light a grill and you get heat to cook your burgers. What happens there is that propane is reacting with oxygen to produce carbon dioxide and water, as we have seen before. But most important, it produces a lot of heat. And that is the heat that's used to cook your burger. So some reactions give off heat and or liberate heat. And here's an example. A combustion, as we have seen before, is an oxidation, a reaction with oxygen. So the example here is carbon reacts with oxygen to give carbon dioxide plus heat. You may recall that is the unit of heat, kilocalories. But here's the key though, it's 94.0 kilocalories per mole of carbon. 1 mole of carbon gives 94.0 kilocalories. That's why it's reported as 94.0 kilocalories per mole. So that's a conversion factor in itself. 1 mole of carbon upon combustion or oxidation will give 94.0 kilocalories of heat. So let's see if we can apply that. So how much heat is liberated when 2.5 moles, notice keyword here again is moles, of carbon reacts in excess here. Conversion factor is right here. 1 mole of carbon gives 94.0 kilocalories of heat. Here's a conversion factor that we set up. 1 mole of carbon gives 94.0. And this is the way we set this up because we need to cancel out here moles of carbon and moles of carbon because we're asked how much heat. So 2.5 times 94 gives 23.5 kilocalories. Conclusion, if you have 2.5 moles of carbon and you react it with an excess of oxygen, you will get 23.5 kilocalories of heat. So be ready to convert or to calculate the heat that's liberated given this conversion factor. Given that conversion factor. Conclusion. Heats of reaction. We have some terms that you need to remember. Exothermic here means a reaction that gives off heat. So the reaction before is an exothermic reaction. Combustion reactions are exothermic. Exo giving off. Thermic here means heat. So these reactions give off heat. Endothermic, on the other hand, is one that absorbs heat. For those of you guys who are in play sports, whenever you have an injury, the sports medic will take out a package and break it and have 2 liquids mixing and put that on the injury, and it gets cold, feels cold. The reason is because it is an endothermic reaction. It is absorbing heat from the body, and hence that's why it feels cold. And of course here combustion is a form of exothermic reaction. So don't forget these terms. Exo, giving off, endo, taking in. Thermic here means heat. This is the end of chapter 4. So the quiz that you'll have on Thursday will be on chapter 4, and the emphasis will be on the last part of chapter 4. So make sure you have your calculators ready and your periodic table ready to take that quiz. It will be an hour quiz, and you have 10 questions, so you have lots of time. So make sure you can, in fact, utilize and understand the concepts and apply the concepts, because on the exam, of course, as you know, you'll have a lot more questions in a lot shorter time to do these questions. So you need to master all of that. So continue to study hard, and I will post another lecture video on starting on chapter 5 soon. But I will also post here the PowerPoints for you to review as you read along in your textbook. Okay? Bye.